Engineers working in metal design a large variety of components. A finished piece of work often consists of a number of separate items joined together in one way or another. The way in which they're joined depends on the materials being used and the component being produced. Many are joined permanently by welding. The welded joint is ideally an extension of the two materials being joined. The weld will have similar characteristics to the parent metal. The best known form of welding is oxyacetylene. It's versatile and used in almost every fabricating shop in the world. It's absolutely essential in welding to work at a very high temperature. The source of the heat can be chemical, as in oxyacetylene, or frictional, or electrical. During the last 30 years, many new welding techniques have been developed to cater for highly specialized processes. The choice, which technique you use, depends on what you want to do and what you need to achieve. Arc welding, or manual metal arc welding, MMA, uses electricity to supply energy. The welder establishes an arc between the end of the electrode and the parent metal at the joint line. The heat generated melts the parent metal and the consumable electrode to form a weld pool. The welder keeps the arc gap constant by moving the electrode progressively towards the weld pool. This is protected by the molten flux surrounding the electrode. The current is controlled by a power supply unit on the right, which gives a consistent electrode melting rate. When the electrode has been melted to a length of about 50 millimeters, the arc is extinguished. The solidified slag or flux is removed, and welding continues with a fresh electrode. Manual arc welding is suitable for mild and medium carbon steels. It's flexible and portable. It may be slow, but it's still widely used in the construction industry, particularly in less accessible areas and in repairing plant. There are limitations. The flux can corrode aluminium, for example. Submerged arc welding, a mechanized technique, is much more satisfactory. An arc is created between the end of the bare wire electrode and the parent metal. As the electrode melts, it's fed into the arc by a servo-controlled motor. This matches the feed rate to the speed with which the electrode is melting, so keeping the arc length constant. The electrode and drive assembly is moved along the line of the joint by a mechanized traverse system. The arc operates under a layer of granular flux, hence the name, submerged arc. Some of the flux melts to give a protective blanket to the weld pool. The unmelted flux is recovered and reused. Because it has a good shielding system and is automated, high currents between 500 and 1,000 amps can be used. This makes submerged arc an ideal way to weld heavy materials. That's why it's found in most fabricating and welding shops. Because it's easy to weld long joints, large components, like this 20-ton girder for a bridge, are ideally suited to submerged arc welding. A number of alternative moving mechanisms can be used. The only requirement is that whatever the method selected, the complete welding head must move at a precisely controllable speed along the joint. Here, the whole assembly is moving on a motorized chassis, which is very simply controlled, making a weld which is easy to reproduce. This is essential, as up to 30 runs may be laid, one on top of the other, to build up an adequate joint. This girder is being preheated so that the metal to be welded will have a uniform starting temperature. When the joint has cooled, the solidified flux is removed and the unused flux recycled, leaving a clean weld. The quality of the weld is excellent, and it needs to be. This girder will eventually become part of a bridge and will have to withstand 60 or 70 years of stress and strain. Techniques have been developed to make arc welding more flexible. These use an inert gas to shield the weld, not a flux. Metal inert gas shielded welding, MIG, is a strong competitor to the manual metal arc process. A continuous electrode is fed at a carefully controlled rate from the wire feed unit through the welding torch. The rate of feed will depend on the DC range being used. The technique is ideal for positional work and the welding of sheet metal, because the low current produces a small weld pool which solidifies quickly and offers minimal penetration of the metal. But the problem with using a low current, between 50 and 180 amps, is that you create an unstable arc. But this can be overcome by a technique called dip transfer. In dip transfer, the electrode melts slowly, and as it's fed steadily into the arc gap closes until the tip touches the weld pool. This causes a short circuit, which melts the end of the electrode, fusing it with the weld pool. This shortens the electrode, and the cycle begins again, repeating itself between 50 and 200 times a second. The type of metal to be welded determines the choice of shielding gas. The nozzle is designed to give a non-turbulent flow of gas over the weld pool at about 12 to 20 liters per minute. The weld is of similar quality to the weld you get with manual metal arc, but there are advantages. There's no need for frequent electrode changes, and there's no flux to be removed. If you increase the current beyond 300 amps, MIG can be used for thicker plates and aluminium. The speed of the electrode feed has to be increased to deal with the higher current, and this gives a very stable arc and uniform melting of the electrode. The process is called spray transfer. Droplets fall regularly from the end of the electrode and are transferred to the weld pool by electromagnetic forces acting down the electrode. The weld is of good quality. Because a higher current is used than in dip transfer, more metal is deposited at a faster rate. On the left, a high current MIG weld done by spray transfer. On the right, a thinner weld done by dip transfer using low current MIG. Although the absence of flux is an advantage, it does mean that all the alloying elements and deoxidizers have to be incorporated in the electrode wires. These are specially produced for MIG welding. For steel, they contain manganese, chromium, and molybdenum to add strength and prevent corrosion. Some wires are copper-coated to increase conductivity. Some even have their own flux core. Their characteristics usually match the composition of the metal to be welded. MIG has opened up many new possibilities in the sheet metal industry where manual metal arc wasn't suitable. It's fast, but the equipment and the welding materials are more expensive. It plays an important role in the car industry. This robotized low current equipment is welding dashboards. The high capital outlay is amply justified. With MIG, you don't have to keep changing the electrodes, and there's no flux to be removed. MIG can be manual, mechanized, or fully automated, allowing one rig to be used for several similar operations. This high current system lays a continuous weld along an aluminium pressure vessel joint. It can be adapted to all sorts of different size jobs. The equipment is set to suit the type of weld and material in hand. One drawback is that the electrode is consumed in MIG welding. But in tungsten inert gas, or TIG welding, the tungsten electrode remains intact. No metal is transferred across the arc, which is used solely as a heat source. Usually, if additional material is needed to build up the weld surface, to fill a groove or form a fillet in a T-joint, it can be fed in separately to the weld pool in the form of a filler wire. With TIG, pure argon is usually employed as a shielding gas, and this is suitable for all metals. As with MIG, the nozzle is designed to match the flow characteristics of the argon. Direct current with the electrode connected to the negative pole of the power supply unit is used for all metals except aluminium. The degree of control which this gives the welder makes the TIG process particularly suitable for the welding of sheet metal. Welds can be deposited in almost every position, but it calls for a high degree of skill and experience. TIG welding is often used in this way for the fabrication of pipework for high-pressure steam lines and for chemical plant. Aluminium and its alloys present a major problem. When the parent metal is melted, the oxide skin is still intact, as its melting point is appreciably higher than the aluminium. As there's no flux in TIG, the oxide skin must be dispersed by the action of the arc. This happens only when the electric current flow is from the weld pool. That is, when it's negative and the electrode is positive. Under these conditions, oxide-free welds can be produced in aluminium. The main drawback is overheating of the electrode, which could eventually cause it to melt. To forestall this, an alternating current is used. During the half cycle, when the electrode is positive, the oxide is dispersed from the molten aluminium. During the negative half cycle, while heat is being built up in the weld pool, the electrode cools. In this way, uniform distribution of heat is achieved, and the electrode can be prevented from melting to any appreciable extent. Although a pure tungsten electrode gives perfectly acceptable welds, it's better to use an electrode with additions of either thorium oxide for DC or zirconium oxide for AC. Both improve arc sticking and stability. Here, TIG is being used to weld prefabricated aluminium piping, which will eventually form part of a large chemical plant. TIG also imparts high-quality welds to stainless steel, pneumonic alloys, and copper. TIG is almost invariably used in the aircraft industry, which is traditionally wary of welding and only permits welds of the highest standard. An alternative method of using electricity to heat a metal is resistance welding. All metals vary in their ability to conduct an electric current. Copper, for instance, is an excellent conductor, steel a poor one. If a high current is passed through a steel bar, it heats rapidly. This principle, exposing a metal to the passage of an electric current, is widely used. A resistance spot weld is not unlike a rivet, And in present-day technology, it's the fastest and easiest way to join two steel sheets of the same thickness together. Although the joint can be made easily, it involves complex and expensive equipment. The two pieces of metal to be joined are placed between two copper alloy electrodes. Pressure is brought to bear on the top electrode, which keeps the two pieces of metal in close contact. A high current is then passed through the joint. The temperature at the interface rises rapidly because it's here there's the greatest resistance to the passage of the current. As a result, the metal melts. Electronic control cuts off the current at the appropriate moment. When the internal molten pool of metal solidifies, it leaves a strong and permanent joint. To give you an example of how simple and efficient spot welding can be, the body of the Mini Metro, cut from mild steel, has several hundred spot welds, all of them made in less than 2 minutes. This very high rate of production is achieved with special jigs and fixtures and banks of electrodes which move forward at predetermined intervals. It's automatic and fully integrated. The joints produced by spot welding can't be made watertight because the bonding isn't continuous. But a continuous seam can be produced by overlapping the spot welds like coins, one on top of the other. Normally disc electrodes are used, one of which is driven by an electric motor. As the electrodes rotate, the metal is moved between them and pulses of current are applied. Each pulse lasts just long enough to produce a spot weld, and the time lapse is so arranged that the spots overlap by about 1/3 of their length along the seam. This technique is particularly suited to the car industry and for producing everything from fridges to cans. The equipment for making metal containers employs pure copper ribbon as the electrode. This passes between the disc electrode plates and forms the seam up the side of the can. As with spot welding, the process is very easily automated. Here, cans are being seam welded at the rate of 200 a minute. All are perfectly sealed and are strong enough to withstand the pressure of aerosol products. In both resistance spot welding and resistance seam welding, the concentration of current at the interface is achieved by carefully shaping the electrode so that the area of contact is as restricted as possible. In projection welding, the weld is made on a projection raised on one of the surfaces to be joined. In this case, it's the contact between two steel bars which forms the projection. Current flowing across the interface is concentrated round the projection, which heats up rapidly. As it becomes plastic and finally fuses, the projection collapses and a fused slug is formed at the interface. The result is very similar to a spot weld. The machines are very like the ones used for spot welding, but the electrodes are replaced by appropriately shaped plates which exert a uniform pressure over the joint area. Projection welding is often used for long lap joints, but it really comes into its own for joining small attachments to sheet metal structures. For example, captive nuts with small projections on one side can be easily attached to a car chassis panel. This process, even when semi-automated, is clean and quick, enabling it to take its place with other production processes with the minimum of fuss. Using electric current is not the only way to heat a workpiece. Friction welding, unlike resistance welding, uses heat produced by friction along with applied pressure. The machine has two chucks, one driven by a motor, the other fixed. The two parts to be joined are clamped into the chucks. The fixed part can be any shape, but the component to be rotated must be round. When the rotating chuck reaches the welding speed, the parts are brought gently into contact. The machine is then stopped, and the weld is formed under pressure. Welding only takes between 10 seconds and a minute and a half. The result is a forged pressure butt weld. There is some excess metal flash, which is removed by machining. Friction welding is widely used in making axle cases for cars and lorries. Although the axles could be forged, in the long run, friction welding is more economical. Setting up is determined initially by trial and error, and the limits have to be carefully defined before production welding can begin. Clearly, it's not a technique suited for one-off jobs, but where there are long runs, it is extremely useful. Friction welding units can be easily installed alongside lathes and other machine tools, and that makes it an attractive proposition for production engineers. As the two abutting faces rub together, friction produces heat, and localized hot plastic zones are produced. With the end load maintained, heat continues to be generated until the whole interface has reached a uniform temperature. At the same time, the plastic starts to flow outwards towards produced. With the end load maintained, heat continues to be generated until the whole interface has reached a uniform temperature. At the same time, the plastic starts to flow outwards towards the periphery, carrying with it any oxide present at the joint face. When sufficient heat has been generated, the rotation is stopped and the end load may be increased. So there are a wide variety of welding techniques. The choice of which one to use depends mainly on the materials to be welded, the kind of joint you want to make, and the working conditions in which the component will be produced. The ultimate aim is to use the most appropriate welding technique for the working conditions available to create the quality of weld specified at the lowest possible cost.